Alright guys, welcome to PreCalculus. This is 2.1.1. So we're going to be um, going over some kind of new terminology. Some of this is stuff you may have seen or heard at least a little bit in the past, but some of it is probably going to be a little bit new, especially the kind of way in which we're going to be kind of introducing it. So to start off here on a problem 1, we have this graph. This is a graph of distance over time. So what I want you to do is, this is Riley and her drive, right? So try and pause the video, write a little story about what would cause these different shapes on the graph. Now you don't need to actually write it down. If you want, you are more than welcome to. But just kind of, in your mind, kind of say, hey, well, what would someone be doing when they're on a drive that would cause the graph to look this particular way? Like what would cause this shape, what would cause this shape, stuff like that. That's the important part, trying to get the connection of the real world and how that is represented on the model. So pause the video, try that out. Okay, so hopefully you have a little story there. So let's take a look at problem number 2. So A is saying, hey, when is Riley's distance from home increasing? Right, so when is she getting further away from home? So what does that look like on the graph? Well, on a graph, she's getting further away from home whenever we're going from close to home, which is going to be here on the axis, to far from home, which is higher here on the y-axis. So whenever I'm going from low to high, as my time is going to the right, so that's when I'm increasing here, right? I got kind of that positive slope, left, right, I'm getting bigger. So it's happening here. It also happens here a little bit too, right? So those are points where I'm actually getting further from home on my drive. And then second question here, well, how about what if the distance from home is decreasing? How is that represented? So if I'm going to be getting closer to home, that's when I'm actually going to be decreasing, right? I'm going from left to right, I'm going down. So here to here, here to here, and then here till here, right? So whenever I'm going down or I'm decreasing, that's when, or I have a negative slope, that's when I'm kind of getting closer to home. So hopefully those are the two things you were able to kind of get off of that. And in part C, is Riley's distance from home ever constant? If yes, explain how you know this. If no, describe what the graph would look like. Okay, so look here, is her distance from home ever not changing? Well, right here is a pretty obvious little patch of when it's not changing, right? Her distance from home is constant. So maybe she stopped at a light. It's kind of a long time you stopped at a light for like 15 minutes, but you get, there's maybe she stopped at the side of the road to go look at a site, whatever, right? She is not getting closer or further from home during that 15-minute period there. Now you could have the argument of, well, at these exact moments where I'm changing, so that peak there, that bottom there, that peak there, we're not changing, but that's just for a brief moment. If you see that, awesome, great, but the main thing we're going to be looking at for that one is this kind of constant flat line. All right, so hopefully those are kind of making sense. So that's really the idea of increasing, right? So this is going to go over the formal definition of increasing. It's really complex for how simple it is, seeing as you guys already kind of know what it means. Like I say, hey, is that graph increasing or decreasing? You could probably already tell me. So the formal definition is this, right? For any values x sub 1 and x sub 2, where x sub 1 is less than x sub 2, if the f of x sub 1 is less than the f of x sub 2 for all values of x sub 1 being less than x sub 2 in that interval, it is increasing. I get that is a lot of math speak and it's really hard to kind of get, but here's what it's saying. If I pick 2 points on my graph, right, my left point and my right point, so that's what it means by okay, one is less than the other, right? So if the y values, their outputs, the one on the right has a higher output than the one on the left, for every pair of points which I pick in some certain interval, it'll be increasing, right? So let's talk about that in the context of this graph. So I'm increasing from here to here. So this is the interval I'm talking about. So I'm going to right now pick 2 points any 2 points you want on this interval where I'm increasing, right? Now one of those is to the left of the other one, so you have a left point and a right point. Is the y value of your right point higher than the y value of your left point? Yes. No matter what 2 points you pick on this interval, that'll always be true. And if that's true, then we're said to be increasing. Okay. Now, you really don't need to use that formal definition every single time you're trying to say, hey, is this increasing or decreasing? I just want to kind of get you used to that notation and kind of how we're going to define that, because it becomes more important when we define more complex things in the future. But if I'm increasing, I'm going up from left to right over the entire interval, right? So I wouldn't say, hey, I'm increasing from here to here, because there's parts in this interval where I'm not increasing. It's like here to here I'm not, here to here I'm not, here to here I'm constant, right? If there's ever spots where you're not increasing, you're going to have to reduce your interval to only the spots where you are increasing the entire time. So, and then we kind of go through the definition here a few more times. I've already kind of gone over that. I'm not going to go over this more in depth, but effectively that's what we just did, right? So if I wanted to change that for decreasing, right, it's going to be the same thing, but my left point and my right point, my left point is always higher than my right point. And if that's the case, then I'm going to be decreasing. So back over here, say this interval here and here where I'm decreasing. Any 2 points you pick on this interval, your left point will always have a larger y value than your right point, or your left point is higher than your right point, so you're decreasing. We're going down from left to right over that entire interval. So that's kind of how we define increasing versus decreasing in the context of these kinds of problems. All right. And then extrema. So extrema is the kind of overarching term for both maximums and minimums. You'll typically just hear them called maxes and mins, right? This is a little bit easier than extrema, but you will see the term extrema used a little bit more in a formal setting. So the tricky part is this kind of gets broken down even further into what are called a local max and min or a global max and min. So the book kind of shows you their definition. What a local maximum is a point where in its nearby area, so like right here, what's the highest point in this little area? Well, it's going to be that little peak there, right? So the kind of size of that area isn't necessarily defined, but you wouldn't do things like, well, in this area here, what's the maximum? Well, oh, it's there, right? For a local max, you're looking for a little bump, right? So in this little bumpy area, it's the highest point in that little bump, right? Over here, there's another local maximum right there. That's my little bump. Local minimum, same thing, but it's a little valley, right? Right there, I got a little local minimum. I got my little valley there. So then we have things called global maximum. So global maximum means, hey, it's the highest point this graph ever gets to. So for instance, this point here is a global maximum because it's the highest point that my graph will ever get to, whereas this one is not because it gets higher over here. This is still a local maximum, but this is my global maximum as well as also being a local maximum. So that's what the term global versus local means. Local, you're just looking for any of the hills and valleys. Global, you're looking at the highest point and the lowest point that a graph will ever get to. So my global minimums are going to be like these endpoints here. Now those endpoints would not necessarily be local minimums too, because there's nothing on the right hand side of it, so we can't really define that area. Same thing here. There's nothing on the left hand side, so I can't say, well, it's the lowest point on this region because there's nothing on the left hand side of that point. They're not going to be really strict on that definition yet, but when you get to a calculus level, they are. So I just want to kind of point that out now. I'm never going to try and trick you on my tests and say, oh, well, this is a global minimum, not a local minimum. Gotcha, that's never my intent. And In truth, we're going to care far more about local mins and maxes than like globals. So as long as you say, hey, hills and valleys, that's mins and maxes, that's what I want you to get out of this right now. So they go over the kind of, or sorry, they don't really go over the definition of it. But one thing that you want to notice here is that at that point, this is a transition point, right? All of those points were special because this maximum is when we transition from increasing to decreasing. This maximum we transition from increasing to decreasing. This minimum we transition from decreasing to increasing, and that'll always be true. That's the kind of alternative way of defining these points is we are transitioning from an increasing to a decreasing from left to right for a maximum. We're transitioning from a decreasing to an increasing from left to right for a minimum. So that'll kind of be our alternate definition. That's kind of why they are important as well. Okay. Okay. Then concavity. This is our kind of last new thing that we're going to be going over. So concavity, you kind of know what concave means. Think of a parabola shape or a curve, right? In a C shape, right? It's the kind of curved part that is said to be concave. So we can have what is called concave up and concave down. Now they have a formal definition. I'll briefly kind of explain what that kind of means, but I'm not going to by any means go heavy into it. So let's say this area here, I'm concave down, right? Fairly easy to, this area here, concave down. Fairly easy to notice because it's like a downward looking cup, right? That's a concave down. So it'd be concave down if I picked any 2 points on this concave down area and I drew a line from one point to the other, right? That line would be under the graph. So we're concave down. When we're in concave up, like over here, if I pick 2 points and I draw my line between them, that point is above my graph. That's how I would technically define concave up. So again, I'm not going to ever get really strict into those formal definitions for us, but I just want you to kind of know because those will pop up once in a while. So concave up is a cup, right? It's going to be going upwards. It's that kind of U shape. Concave down is a frown. It's going to be going down like an N shape. Okay, so on our graph here, we're from here to here, we're concave up, right? So we can kind of see that upward shape to it. And then we do a transition here to now being concave down. And then over here, it looks like we're concave up. Then we're going to change maybe about here to being concave down. So it's quite often that you're going to see concave ups and downs kind of being linked, right? And then there's going to be that point where they change from down to up, right? That point is what's called an inflection point, and they're going to define that here for us. Yeah, a point of inflection, more commonly called an inflection point. So there is exact ways to find those and where they are exactly. For our purposes in this class, I'm not going to have you find those because that is a calculus type problem, and we're not there yet. So in general, just kind of look at about where it's happening, right? So it looks like maybe it's happening here at like 0.5. It seems to be a kind of good place for that to be transitioning. Over here, from here to here, it looks like maybe it's like 1.75, right? A general rule, you can kind of go halfway between those points and say, hey, that's about where it's going to be happening. That's not always the case. For instance, over here at the very start, it's actually happening a little bit further right than right in the middle of this minimum and this maximum, right? But in general, if you just kind of need to kind of give it a point, it's really hard to tell. Just go kind of halfway. So like here, between 1.5 and 2, halfway between those is that 1.75. That seems like a pretty good place to say where that concavity is changing. So either give me a good estimate or just kind of go halfway between those. That's where that concavity is going to be changing. right? Things that are flat, like this constant area here, where we were not getting any further or nearer to home, that has no concavity. Flat lines, be them horizontal or even angled, are not concave at all. A concave has to have some curve to it for it to be concave. Okay, so those are the main things we've kind of, main new kind of definitions we've done. So what I want you guys to do now is try and answer these questions in relationship to that kind of graph and stuff there. So A, so go ahead and pause and then come back here. All right, so A, how fast was Riley driving when she was 30 minutes into her drive? So 30 minutes in, that's at 0.5. How fast was she driving? Well, it's kind of hard to tell her exact speed because this is distance and this is time. So if I want to kind of estimate that, well, at this point she's 8 miles away, and that took her 0.75 hours. So she's going 8 miles in 0.75 hours. So if I do 8 divided by 0.75, I get 10.6 repeating, or 10 and 2/3. So almost 10 miles per hour on average going from here to here. Now, is she going that speed consistently? No, right? You see from here to here, she's speeding up, and then she begins to kind of slow down. So we're kind of doing an estimate or an average here. So her average over that time was 10.6. So we're going to say, hey, maybe it's 10 or 10.6, maybe a little bit faster because this seems pretty steep. However you want to kind of estimate that, but in the 10.6 range is a pretty good estimate for that. Okay, was Riley's speed ever 0 miles per hour? Well, we could say, yeah, here to here. I mean, this theoretically could not be 0 because she could be driving on some curve that is literally the perfect curve of a radius from home. Odds of that is very, very low. So we're going to assume that her speed was 0 there. Her speed was also 0 for just a brief moment at these peaks in these valleys, right? Because that's where we're going from increasing distance to decreasing distance, or we're speeding up to slowing down, things like that. So it must have happened at some points there. Was Riley ever speeding? Well, looking here, probably not, because again, we were averaging like 10.6 miles per hour from here to here, right? Here to here, we're having a change of 1, 2, 3, 4, 5 miles in 15 minutes. So really, we're probably not speeding unless this town has some very, very low speed limits on it. When did Riley ever go from speeding up to slowing down? So she was speeding up and then she was slowing down. So she's speeding up here, right? And then she actually starts to slow down here. Now it's easy to think or to say, hey, I'm changing speeds here to here because I'm going increasing speed to decreasing speed, but this is not a speed y-axis. This is a distance y-axis. So I'm speeding up as I'm driving further away, and then I start to slow down. So the concavity is actually what I'm looking at here. Because if you think about speed, your speed is your kind of slope here, right? It's the rise over the run. So here, my slope is increasing, and then here my slope is decreasing. My slope actually keeps decreasing all the way here. Because again, that's going to be related more to our concavity than it is going to be related to our increasing versus decreasing. Okay. And how far did Riley travel during her 2-hour drive? So it's about how we can calculate this. So again, this is in miles on our y-axis. So from here to here, this first part, she drove a total that was 8 miles, and then she drove 2 more miles before she stopped after kind of coming a little bit back towards home. So that's 8 and 2, we're at 10 miles. And then here to here, we're going 5 miles, so that's 15 miles. And then we're going back up 4 miles here, so we're at 19 miles. And then we're going down 5, so we're going to be at 24 miles there total, unless I did some math in my head wrong, which I may have, so sorry. So that's how we can kind of go through those. So main thing that I want you to kind of get out of that is kind of what all of those things kind of represent. So our speed is being represented by the slope here. So I'm accelerating when my slope is increasing. I'm decelerating when my slope is decreasing, right? I'm getting further from home when I'm increasing. I'm getting nearer to home when I'm decreasing, stuff like that. So keep those in mind. It's once you start to get a better feel for it, it'll be a little bit easier. But knowing the units of the graph is very important, and that's kind of why. Because if this was a speed to time graph, it'd be very different than this current distance to time graph. Okay, so what I want you to do now is in your head sketch each of these graphs, A, B, C, and D. So then pause and then come back here. All right, so part A, I'm increasing and I'm concave down. I'm going to turn around because it's hard for me to do this mirrored and still do it correctly. So if I'm increasing and I'm concave down, so I need to be going up and to the right, but I need to be concave down, so it needs to have that kind of curve there, so I need to be kind of doing that. So it's kind of that shape, right? Or that shape, right? Where I'm increasing, but I'm still concave down. So it's that kind of side of a parabola shape, right? B, I'm increasing, but I'm concave up. So that means I'm going up. I need to be kind of concave up. So I'm going to be having that kind of angle there, right? Decreasing and concave down. So you'd be decreasing, but concave down. So my curve is going to be like that, and I'm going downward. Right? Decreasing and concave up. So that would be kind of like that, right? I'm decreasing, but I'm concave up. Hopefully those kind of make sense as long as you can kind of see them in your head. That's the important part. Okay, and our last thing is we want to try and describe this, or sorry, not quite our last thing. So let's talk about these regions here. So here to here, I'm decreasing and I'm concave up. Here to here, I'm increasing and concave down. Here to here, I'm increasing and concave up. And here to here, I'm decreasing and concave down. So hopefully those kind of make sense as far as what those are going to look like. Because concavity and increasing and decreasing people mix up or think are the same incorrectly quite often. So let's kind of watch for those. All right. And then what I want you to do is try and sketch each of these kind of criteria for me. So first one, have it be increasing only from -1 to 4, and it needs to be concave down whenever x is larger than 2. And then once you've done that, go ahead and try and sketch a graph that is decreasing from 2 to 5. It is concave up when x is larger than 3, and it's concave up when x is less than -1. So try and draw a graph that meets those criteria. All right. With that, here is our homework. So we're going to be doing 9 through 16. And I will talk to you guys next time.